Okay, today we're going to be talking about displacement or translation vectors. So we know that a vector is a quantity that has both a magnitude and a displacement. We can call the displacement of a vector its translation. So say we have point L and we go to point M. The magnitude of this line is the displacement of this vector quantity here. Now we can call this vector LM, with a little arrow above it, or we could give it the name A, and that A would be in bold, or we could call it A with a little squiggle. So obviously when you're writing on paper you can't really make it bold, so to denote a vector you'd put a wee squiggle underneath it. The vector, so we had vector A to B, and AB is given the value 3, 1. The value 3 means go 3 in the x direction, and the 1 is 1 in the y direction. So the top number is our x, the displacement in the x direction. The y coordinate here is our displacement in the y direction, and if it's going in this direction, so say you had a vector like that, you would have a minus x, y, so your vector would be minus x, y, and similarly a vector that went down the way, so A to B, this would be again minus x, and it would be going down, so minus y. Now this is in 2 dimensions, and we live in a 3-dimensional space. So we have our coordinates y, we have x, but we can also have a third axis z to represent 3-dimensional space, and we can have some point in our space here, P, with coordinates x, y, and z. Now let's say we have a vector at point P, and its coordinates are 1, 3, and 7, and it moves to point Q, which is 5, 3, 8. What is the displacement vector PQ? So to get PQ, we would take the values of P, 1, 3, 7, and then add them to Q, 5, 3, 8. Subtract them. I've written these the wrong way round, sorry. It's hard to draw them in a 3-dimensional space. So we've got 1, 3 and 7 would be way over here, and then you're moving to Q, which would be 5, 3 and 8 way over here somewhere, and so you've gone from P to Q. So we do Q minus P, which is 5, 3, 8 minus 1, 3, 7. So that's going to be 4, 0, 1. So that is the displacement of the movement from this point P to this point Q. Now, a wee bit more on notation. So say we have this vector A. And as I said, we can write that in bold, or we can do a wee squiggle. Then we have another vector here, which is B. And then we've got another vector here. And this time the arrow's in the opposite direction, so that's C. So vectors A and B have the same direction but not the same magnitude or length. And so if vectors A and B are parallel, but not equal, so not the same vector, we can write A as some scalar of B. Now in fact A is half of B, so in our example A is half of B, so B is equal to 2A. Because this is a scalar, they are we know they're going to be parallel. Now vector C is 3/4 of length B, but in the opposite direction. So C is equal to minus, oops, that looks like an A again, let's just rewrite that better. So C is equal to minus 3/4 B. Now, so in general, parallel vectors are a scalar multiple of each other. So A is lambda B. Those two vectors would be parallel. So combining displacements. So say we have vector A here, and it goes to vector B, to point B here. And it's given by this displacement. So AB is equal to 4, 2. And then we have displacement over here. And this is point C. And BC is equal to 3, 7. Now we want to find out what the resultant overall displacement is. Here, so AC. So AC is called the resultant vector. And it's given by adding AB plus BC. So 4, 2 plus 3, 7 is going to be 7, 9. So in vector addition, say we have points A, B and C, the vector AB plus BC is equal to AC. Now, if you were to turn around and go back to CA, we'd be back at point A, and AC plus CA would equal 0, 0. Because if you go up, if you've gone from A to B to C, that's the same as just going from A to C, and then you get your resultant vector. But if you go back to point A, there's no net displacement, so the addition of AC to CA is 0, which is a bit laboured to point the obvious out. Therefore, CA, which is the opposite direction from AC, must be the negative, is minus AC. So in this case, it would be equal to minus 7 minus 9. So this fact is always true. This fact holds for all vectors because they have the opposite direction. Now, we can also have vector addition. So A minus B is the same as A plus minus B. And A plus B is the same as B plus A, which means vector addition is commutative. Okay, let's do an example so that we can see how this works in practice. So we're going to have a quadrilateral. So we've got P, we've got S, and they're linked with some vector B, and up here you've got Q, and over here you've got R. Now, there's a vector between P and some point M here. This is A. Now, M is the midpoint of SR. And we know P, the vector PQ is A, PS is B, and PM, so this vector in the middle, we're given as being a quarter 2A plus 5B. So firstly, find an expression for SM. Secondly, find an expression for QR. And finally, describe the quadrilateral. PQRS and justify your answer. So, let's look where we want. What do we want? We want to find SM. But if you think about it, PS plus SM is going to be equal to PM. So PS plus SM is equal to PM. So we can just do some simple algebra here. So SM must be equal to PM minus PS. Now we know what PM is. And we know PS is just B. So we can tidy that up. So it's just going to be a half A plus. Oh, so I've put the 4 in there already. Oops. Plus 5 over 4B minus B, which is going to give us a half A. Now it's going to be 5 over 4 minus 1 is just a quarter B. Now, put the other one here. We want QR. So QR is over here. And now if we go PQ, QP plus PS plus SR must be the same as QR. So you just follow the route between Q to R. So QR must be the same as QP plus PS plus SR. Now QP is the opposite of A, is minus A. PS is just B. And SR is twice, remember this is the midpoint, we know what SM is, but this is the midpoint, so it must be twice SM. So this is plus, SM is what we've just got here, so this is going to be plus A plus a half B, so the A's cancel, and we get 3 over 2B. I've got room for this one, so let's look at QR and PS. So QR is equal to 3 over 2 PS. Therefore, QR and PS are parallel. Therefore, this implies PQRS is a trapezium, because you've got these two lines which are parallel and these two lines are not, so it's an irregular trapezium. Let's do another one. Find so firstly we need to explain, I forgot to tell you this, so the magnitude of a vector. So the magnitude of a vector is the length of the line that represents the vector, and we can find this out by using Pythagoras. So if we had a vector that was 3 along and 2 up, this vector here, A, would just be 3, 2. But we can find the magnitude of that vector, so that's just a right angle triangle, so we can just use Pythagoras. So let's do an example to show this. So find the magnitude of the vectors A is 4, 3, B is minus 3, 4, and A minus B. And then part B, if P is equal to 5, 0, 8 and Q is equal to 1 minus 1, 8 minus 3, find the magnitude of P plus Q. Okay, so part A. So we want to find the magnitude of A. Now the notation that we use for the magnitude is we put is same as the notation for modulus, is this. So here we've got a vector which is 4 in the x direction and 3 in the y direction. So just applying Pythagoras, you'll have 4 squared plus 3 squared, which is the square root of 25, which is 5. And similarly for B, you have minus 3 squared plus 4 squared, which again is root 25, which is 5. Now A minus B is 4, 3 minus 3, 4, which is 7 minus 1. So the magnitude of A minus B is going to be square root of 7 squared plus minus 1 squared, which is root 50, which is 5 root 2. Now B, we want to find P plus Q. So this is going to be 5, 0, 8 plus minus 1, 8 minus 3. So that's 4, 8, 5. Now we do this in exactly the same way as we do with a two-dimensional vector. This time we just have 3 values in here. So we have 4 squared plus 8 squared plus 5 squared, which is root 150, and we can't really simplify that anymore, so we'll just leave it like that. Next, we're going to define what a unit vector is. So a unit vector is any vector of magnitude 1. And we denote it as A in bold with a little hat over the top. I'll put the wee squiggle underneath this to show it's a vector. So we can take our vector and we can turn it into a unit vector. So to find unit displacement vector in a particular direction, firstly we find the magnitude of displacement, and then secondly we divide the components of the vector by the magnitude. So if you have some vector P with values P1, P2, P3, then the unit vector would be P1 divided by the magnitude of the vector, P2 divided by the magnitude of the vector, and then P3 divided by the magnitude of the vector. Let's do an example to make that more clear. So we want to find the unit vector in direction √5 over 2. So this means we've got a length here, √5, up to, and this is our magnitude here, and the magnitude would be 3. So the magnitude of √5 over 2 is √5 squared plus 2 squared, which is √9, which is 3. So that's our √3. But our magnitude here is, and this is just one, let me draw that in a different colour. So when we get this bit here, which is just 1, what's the value for x along and y up? So it would be √5 over 3, and this would be 2 over √3. So our unit vector of √5, it's not a fraction, sorry, √5 2 is going to be √5 over 3 and √5, nope, not √5, 2 over 3. Let's do another one. So we've got points A, B and C. Are such that AB equals 3, 4, 1 and BC equals 11 minus 2 minus 1. Find the unit displacement vector in the AC direction. So we have AB, oops, that's a rubbish line. A, B, B, C. I was meant to slope down a bit, but it didn't work very well. And then we have A, C. So A, C equals A, B plus B, C. 3, 4, 1 plus 11 minus 2 minus 1. So that gives us 14, 2, 0. So the magnitude of AC is 14 squared plus 2 squared plus 0. And that is going to give us the root of 200, which is 10√2. So the unit displacement vector is going to be 1 over 10√2, and that's 14, 2 and 0. You can take this out here as a scalar quantity because you're going to multiply each component of the vector with it, and it just makes it a bit tidier to write. So I hope that helps.